Hello and welcome back to my favorite people, and thank you for watching this lecture video. In the last couple of lectures, we were talking about oxidation reduction of alcohols, and we practiced good number of examples. Now, in this lecture, I'm going to try to show you the vital role of this type of chemical reactions in our body, how important they are, and when it comes to respiration process or producing ATP in order to move and stay alive. And I said this one many times in my previous lectures that I said whenever we're creating a positive or negative charge, we would try to distribute it over a big volume. Why? Because if the ratio of charge over volume goes down, and the system will be, system can easily handle that positive or negative charge, and the species will be stable. And also, you will see plenty rings that, or double, triple bonds there. The reason for it because we can have resin structure. So anything that facilitates in the moving the positive or negative charge over other atoms, it will help the system to be more stable. And as you see, the structure that you have in front of you is for NADH. It's a giant molecule with plenty rings and double bonds. And the active side of this actually this reducing agent is here. This is the active side, and I want you to zoom on carbon. And which carbon? Let's pick this carbon, okay? And maybe I should pick different color, okay? That carbon. And what's the reason behind it? The reason behind it is if I zoom there, that carbon right now, it has sp3 hybridization. Okay, and what's the oxidation number of carbon? And if I assume these two carbons are identical, and let's say they don't have much difference in, or they're not that different in electronegativity, they are different in fact, and but not terribly. And the carbon that we have in the middle, that carbon is attached to hydrogens. And I know electronegativity of carbon is higher than electronegativity of hydrogen. So I can say for now, hydrogen, that carbon, and it's going to have -2 as oxidation number. Why? Because hydrogen is going to be +1, this one +1. So, really like a rough assumption is going to be this. Carbon in the black color, it has -2 as an oxidation number. Okay, and let's follow that carbon and see what will happen to that carbon over time while we are running chemical reactions. Okay. And NADH, we said, is a good reducing agent. And why is it a good reducing agent? Because it can actually give, it can give this hydrogen to any species, to anywhere that it is looking actually for electron. And then, so if we take that hydrogen with 2 electrons, that's going to be hydride. So I'm going to say this is hydride. And hydride will reduce the oxidation number of any carbon that get attached to it. This carbon oxidation number for it is a +2. How do I know? Because oxygen is -2. Now, if hydrogen comes to it, hydrogen is coming with a negative charge, and the positive charge on carbon is going to go down by 1. So that's the reason I'm going to call NADH reducing agent or reductant. Okay, reducing agent or reductant. And what will happen to the H when we give it, to the carbonyl? And very soon that carbonyl is going to turn to OH. It will turn to alcohol. Now, if we have water or acidic H somewhere, we will take an acidic H from the from the acid, and it will turn to alcohol. And of course, we get also the base. So the production of the product of reducing ketone or say aldehyde, it will be an alcohol. Okay, it can be it's going to be alcohol. If it's aldehyde, it will be primary alcohol. If it's a ketone, and it will be a secondary alcohol. In this case, it will be because we started with ketone, it will be a secondary alcohol. Now let's zoom on the same carbon. This is the carbon that we were talking about. This is the carbon. Now, okay, that carbon, it has sp2 hybridization. Okay, and remember, electronegativity of sp hybridization is higher than electronegativity of sp2 and higher than electronegativity of sp3. So our carbon used to be sp3. Now we turn it to sp2. So this carbon now is thirsty of electron. Also, check nitrogen. Nitrogen shared the lone pairs that had. Nitrogen used to be sp3. And what was the charge on it? 0. No charge on it. Formal charge was 0. Now we turn nitrogen to +1, and the hybridization is sp2. Okay, so now I got 2 centers that they are sp2. We used to have sp3, 2 sp3s, and we know sp3, they have less electronegativity than sp2. So I'm going to say the NAD plus is going to be really, really thirsty of electron. What does it mean? It means it can behave as an oxidant or oxidizing agent. Oxidant or oxidizing agent. Okay, so NADH, when it has H, that means it has the reducing agent, it has the hydride, and hydride, whatever goes, it will reduce that compound, it will reduce that carbon. Okay, we turn it to NAD plus. That means this one does not have H anymore, it has a positive charge, it's not going to be that stable, and so it will be looking for hydrogen to turn neutral. Okay, now I had the ketone, I reduce it, and I turn it to alcohol. Is it possible to oxidize alcohol and turn it to ketone or aldehyde? Yes. We practiced a good number of examples in the last couple of lectures. And the question is going to be, who's going to do it in our body? And in our body, again, NAD plus is capable of doing that one. So now I have a carbon with sp2 hybridization, nitrogen also with sp2 hybridization. Nitrogen, it has a plus charge, so nitrogen is not going to be happy. Nitrogen is an electronegative element. It should not have a positive charge. It wants to get electron. Now, where can I get the electron? I can find it in alcohol. We're going to take a hydride from it, so this time minus H, minus hydride, H minus or hydride. So we're taking hydride, and this hydrogen is going to take those 2 electrons, and it will give them to the NDA plus. So now we turn this carbon back to sp3. Now what will happen to the to those 2 electrons? I'm talking about those two bonds. Those 2 bonds, they will travel and until they make it to that technically nitrogen. Now our nitrogen has 0 as formal charge, and the hybridization is sp3. So now it's completely saturated, both carbon and nitrogen, and the hybridization is sp3. So what does it mean? It means we rebuild the NADH. So this reducing agent now it can be used to oxidize, to reduce another ketone or aldehyde. Okay, so NAD plus will oxidize alcohol, and it depends whether it's a primary or secondary. It can turn it to aldehyde or ketone. And while this one is happening, we will get NADH back. Okay, we will get it back. And this cycle is really important in citric acid cycle or Krebs cycle, or when it comes to respiration reaction. And in that case, in the citric acid cycle, and at the end, technically, we will make ATP or we will make energy. How? We start with a sugar molecule, we process that sugar molecule inside mitochondria. I think I believe that's the name for it. And so it will process it, and at the end we will get ATP. And ATP is the molecule that we use it for, like technically to store energy in it. So ATP is really unstable molecule, and because it's unstable molecule, it has plenty of energy that we can use it anytime we want. Now, question is, we have a ring, and a ring that I showed you. If I go back, okay, for example, when we got this ring here, we got carbon that it has sp2 hybridization. Okay, and you assume oxidation, and oxidation of those type of carbon is going to be really hard. And or if there is alcohol, if I replace OH if I replace hydrogen by OH, that should be really hard, and it should not be easily done. And nature is smart enough and managed to come with some solution and to do it. And so we said for oxidation, we need to have alpha hydrogen attached to the alpha carbon. Okay, and that was the reason actually the tertiary alcohol will not go through oxidation reactions. So when I look to phenyl also does not have alpha hydrogen. But if you expose in phenyl to a strong oxidizing agent, we can get this type of product. We get double bond here, double bond there, and we will have those 2 carbon. This compound, you call it benzoquinone. Okay, benzoquinone now got oxidized, lost good number of the electron. How do I know it? Look to this carbon. This carbon is attached to OH. OH is -1. Okay, so this carbon should be +1, but now is attached to oxygen that is -2. So this carbon should be +2. So just by looking to this carbon, oxidation number of carbon went up by 1 degree. So we lost 1 electron, and we lost 1 electron on that carbon. And also here we lost 2, we lost actually more. Why we lost more? Because we used to have H. Now we have Oh, okay. So from -1, now we turn it to +2. And the oxidation is way higher actually than just one, losing one electron. Now, if you take this compound and reduce it, okay. If we reduce this compound, we will get such a thing. Get OH and OH here, and this compound will be aromatic. But if you oxidize it, you can get this one back. Okay, so benzoquinone, it can get reduced and turned to hydroquinone, and the hydroquinone we can oxidize it and turn it to benzoquinone. The nice thing with these two compounds is that we can use them as kind of like a battery or source of energy. We can store electron inside of it. Whenever we want those electrons, we can get it back from carbon, and that way we can reduce, for example, reduce a carbonyl group or oxidize an alcohol. And your body does such a chemical reaction. Again, I said this is really critical when it comes to respiration and reaction.